Hi, everyone. So we just went from Cartesian to polar. Let's now go from polar to Cartesian. So let's say that you're here at the palm tree at the origin, and this treasure map tells you what direction to go in. That's theta, the direction angle, between 0 degrees and 360 degrees, and also how far to go. We can denote this by the magnitude or length of V, or r. So let's say you're given r and theta, these polar coordinates for this point over here, the terminal point where you can get your tickets. But let's say that you're looking at a map and you want to know, well, how far east do I go? How far north do I go? What are the Cartesian coordinates of this point? How can I write this vector in Cartesian component form? I guess I should write this in red maybe, or purple. Okay. How do I write the vector in Cartesian component form? When you think Cartesian, you might want to think cartography, the science of map making, going east and north. Now, cartography was not named after Descartes, but it's convenient that these sound alike. How do we go from polar in blue to Cartesian in red? In a way, this is faster. If you know SOHCAHTOA, remember SOHCAHTOA, the ancient curse from chapter 4. Okay, let's say that we're given this angle. Let's say we want to know A or X. And then later we'll look at B or Y. But let's say that we want to know A or X. Well, we're given an angle and the hypotenuse, and we want to know about the adjacent side. What relates angle, adjacent side, and hypotenuse? That sounds like cotomy. Cosine of theta is adjacent over hypotenuse. All right. And likewise, what do you think is going on here? Okay, to get the opposite side, B or Y, what relates an angle, the opposite side, and the hypotenuse? That's going to be sine. Sine is opposite over hypotenuse. So it looks to me like we're going to need cosine in order to get A or X, and we're going to need sine in order to get B or Y. SOHCAHTOA. So again, cosine of theta is A or X over the length of V. Again, you might think this more easily as cosine of theta is X over R. For practical purposes, that might be easier. Cosine of theta is X over R. Therefore, X is R cosine of theta. The X component here, the horizontal component, A or X more generically, is given by R cosine of theta. X equals R cosine of theta. Likewise, I'll put this in purple. What about sine of theta? Sine of theta is opposite over hypotenuse. So it's going to be B over the length. You could say Y over the hypotenuse, R. Sine of theta is Y over R, opposite over hypotenuse. So Y equals R sine of theta. And in fact, in calculus 2, you tend to think of it this way, converting from polar to Cartesian. You tend to think of it this way. X equals R cosine of theta, and Y equals R sine of theta. That's an easier way to think of it. X equals R cosine of theta. Y equals R sine of theta, which means that when we resolve this vector into Cartesian component form, A comma B or X comma Y, we can do it as a one-liner. It's basically R cosine of theta comma R sine of theta, where R is the length of V, the magnitude of the vector. So in a way, this is easier. And the quadrants work out in everything. All right. It wasn't like that tangent deal up before. Again, this is literally a resolution. These formulas allow us to resolve a vector into its Cartesian, horizontal, and vertical components. We're resolving a vector. All right. Here's an example. Out in the flat desert, so it's not on a hill, out on the flat desert, let's say North Korea shoots a projectile at a speed of 50 miles per hour. That's pretty slow for a missile, but let's say that the initial speed of this missile is 50 miles per hour. That's a scalar. And the angle of elevation, this direction angle, is 30 degrees relative to the flat desert. Okay, so from this polar information, 30 degrees, that's the direction angle, that's theta, right? R, or the magnitude of v, the length of the vector, is 50 miles per hour. That's the scalar. Remember, this speed here is the magnitude of this velocity vector. And this is just the initial velocity vector. We're not being too ambitious. We're not trying to trace the trajectory of this vector in the long run, okay? We're just looking at what's happening with this missile at the very moment that it's fired, okay? Just at time t equals 0. We're not looking in the future. This is the initial velocity vector, v. So we're going to resolve this vector into its Cartesian component form, into the form angle brackets a comma b, or x comma y, Cartesian component form. Well, I showed you the handy dandy formula, right? Again, r, or the length of v, the speed is 50 miles per hour. Theta, the direction angle, is 30 degrees. This is the polar information, remember. So this here is the polar information, and we're going to convert to Cartesian. We want the Cartesian components. Okay, so the vector v is a comma b, or if you wish, x comma y. Oops. So again, up here, this is polar. Okay. And then over here, this is going to be Cartesian. Here we go. Cartesian. Okay. And we're going to resolve this vector into Cartesian components. A comma b, or x comma y. X is r cosine of theta, y is r sine of theta. So x is 50 cosine of 30 degrees. Y is 50 sine of 30 degrees. These are known special angles. You shouldn't even have to use your calculator. 50 times cosine of 30 degrees is root 3 over 2. And then 50 times sine of 30 degrees is 1/2. You better know that, right? A physics professor asks you, what's sine of 30 degrees? You say, sir or ma'am, it's 1/2. Okay. Simplify, we get 25 root 3 for the horizontal component, 25 for the vertical component. Technically, we should put the unit miles per hour for both. A lot of books don't do that, but technically, these two components share the same unit, miles per hour, as the hypotenuse here, r. All right. So now what does that mean? That means that the horizontal component of velocity is 25 root 3 miles per hour, and the vertical component of velocity, initial velocity at time 0, is 25 miles per hour. Now what does that mean? Okay, what does that mean? That means that if we assume that the vector keeps on going in this direction and with this speed. Now, I realize that Earth's gravitational pull will not allow that. Maybe this is happening in outer space. Imagine this is happening in outer space. Law of inertia, okay? This missile is just flying out in outer space. So same direction angle, same speed. Okay. Well, then, if you imagine lights coming down, like on Earth, right? Imagine the sun, it's at noon, the sun's rays are coming down, okay? And we're looking at the shadow of the missile along the desert floor, all right? Basically, the horizontal component of velocity tells us how fast is this shadow moving along the desert at time t equals 0, right? So it's at that instant, okay? At that instant, at time t equals 0, at the time the missile is shot, how fast is the shadow moving along the desert? Right. Actually, even when you consider issues of gravity, that tends not to change too much over time. It's really the vertical aspect that changes when you consider the gravity aspect. Okay, again, you could think of this in outer space. Okay, now what about the vertical component of velocity? Still, it's easy to set up analogies on Earth. Imagine that there's a big wall here, okay? All right, and imagine a bunch of floodlights over here. You have a bunch of lights coming here where the light rays are going perpendicular to this wall, okay? So you have the shadow of this missile up against this wall here, right? And the shadow is moving, okay? So at time t equals 0, okay, how fast is this shadow moving up this screen, this wall here? That's kind of the idea. Horizontal and vertical components of velocity. How fast are the shadows, the projections moving on this horizontal line over here, on this vertical line over here? You talk a lot about projections later on, especially in linear algebra, Math 254. Okay, we're resolving this overall velocity vector into horizontal and vertical components. So if you're talking about driving a car, this velocity vector is in the direction that you're driving your car in. Right? And then you could talk about shadows relative to these guardrails, maybe. Next up, okay, computations, working with the numbers. How do we work with these component forms for vectors, these Cartesian component forms, and how can we apply operations like scalar multiplication, addition, and subtraction using these Cartesian component forms? We're going to work with numbers. We've been talking about geometry and trigonometry. We're going to go more with the numbers now.